Have you ever wondered how rocks affect the rest of Earth's systems? I mean, do they affect climate? Do they affect life? Well, that is exactly what we'll be talking about in this video. Specifically how the lithosphere affects climate and kind of biogeochemical cycles. Don't be scared by that word. I just made some recent videos about biogeochemical cycles, which you can check out. They're very simple. It's just kind of the cycles that elements go through in order to go through the biosphere, life, the atmosphere, air, the hydrosphere, water, and cryosphere, ice, as well as the geosphere, which includes the lithosphere, and this is just rocks on Earth. So I'll talk a little bit about, well, first off, what the lithosphere is, why it's important, why it interacts with these elements, and things that then go on to affect climate and how it does so, and the potential impact the lithosphere will have on the current climate change trend. So let's get started. So before we start talking about the lithosphere, let's just define what it is. So first off, when Earth formed about 4.55 billion years ago, as it was cooling down from being really hot and molten, it formed layers because the constituents of inner Earth separated out based on density. The denser ones sinking to the core with very iron-rich material, and the less dense silicate-rich materials at the surface. But what exactly is the lithosphere in terms of like which layer is this and why is it so important, and what is the difference between the geosphere and lithosphere and how they're used? So the geosphere is essentially everything that makes up Earth that is rock. So the crust, the mantle, the core, all of it is the geosphere. Geo means Earth. The lithosphere, on the other hand, includes only, it's a layer of Earth that includes the uppermost mantle and the crust. It is often used interchangeably when discussing surface biogeochemical cycles because the lithosphere, the outermost layer of Earth's geosphere, is in direct contact with the atmosphere, the biosphere, and the hydrosphere, kind of helping drive those cycles, drive the transfer of elements between those different systems. But other layers of Earth's geosphere also play very important roles in the biogeochemical cycles. For example, the asthenosphere, which underlies the lithospheric layer, which the lithospheric layer is broken up into lithospheric plates, and these undergo plate tectonics because they ride on the more plastic or malleable asthenosphere. And plate tectonics heavily affect climate and biogeochemical cycles, and thus life, over geologic timescales, of course, because they move very slowly. So essentially the lithosphere is the outermost layer, and it is what we kind of refer to when we're talking about the geospheric or the rock portion of the biogeochemical cycles or the systems that the elements are cycling through. However, of course, all the other layers play important roles as well, just not as direct and obviously on very long timescales. Now, in the last video about how the atmosphere is structured and circulates and how that affects climate, we talked about how the composition of the atmosphere heavily affects both life and climate on Earth. But atmospheric composition also greatly affects the lithosphere, or rocks on Earth. How? Well, weathering is the main way. Before we get into weathering and how it works and how it affects the lithosphere, allow me to explain what the lithosphere, or this outermost layer of rocks on Earth, is mostly made of. And in short, that is silicates. Like I mentioned earlier, Earth's outer layers are very heavily rich in silicates, and what silicates are just basically any mineral containing silicon and oxygen, and these are the two elements that are obviously, as you can see, the most abundant in Earth's lithosphere. And these elements go on to make all these really common minerals in the lithosphere, and you can see quartz and feldspar are the most common, and then there's some other silicate minerals that also are present and abundant in the lithosphere, and then only 8% of the lithosphere is non-silicate minerals, so minerals that don't contain the silicon and oxygen group at the end. But don't worry about the chemistry really of any of this. We're not going to get into it that much. The important detail here about the fact that silicates make up most of the lithosphere is that these types of minerals weather or dissolve incongruently, meaning that certain elements in those minerals dissolve out before others. So they don't just all completely dissolve at once, certain components leave the mineral and certain components don't. And that leads to the mobility of some elements and the kind of stability or limited mobility of other elements in the lithosphere. And that greatly affects the composition of the lithosphere, the distribution of elements in the lithosphere, and the interactions that the lithosphere has with the atmosphere, the hydrosphere, the biosphere, and other components of the geosphere. Now, weathering can include both physical and chemical breakdown and alteration of rocks, and erosion is the transportation and removal of weathered material. In other words, weathering is kind of the preparation process for then erosion to happen. And I talk about the differences between weathering and erosion way more detailed in my weathering versus erosion video, which I will link up to the top right for you if you're curious. But essentially, the types of weathering include chemical, physical, and biological. I will talk today in this video briefly about the chemical and biological weathering pathways, because these are the ones that really affect the composition of the lithosphere and thus the interaction that the elements have from the lithosphere with other systems of Earth. Now, chemical weathering contributes the most to lithosphere, atmosphere, ocean interactions and cycling of elements through each of these systems, because it involves the chemical alteration of rocks and minerals through typically rain or rain infiltrating soils or sediments or marine water or river water or lake water. Any water flowing over or into rocks can chemically alter it. And this can happen in a few different ways. One way that rocks can become chemically weathered is through hydrolysis. This essentially just dissolves the mineral by reaction with water. Essentially, ions can get kind of surrounded by water molecules and disassociate with the mineral. And this happens to feldspar. Feldspar transforms into clay minerals upon hydrolysis reaction. And then another way that minerals can become chemically weathered is through oxidation. Because our atmosphere contains oxygen, which is a relatively reactive oxidant, it oxidizes things or essentially takes their electrons away. This can cause the oxidation of things like iron minerals. Iron minerals can react with oxygen to become oxidized and thus just rust. Rusting and oxidation are the same thing. And through carbonation. The carbon dioxide in the atmosphere can react with water to form carbonic acid, which can then either rain onto minerals or flow over minerals or something to contribute to dissolving them. Now, like we just talked about, the minerals in Earth's crust are mostly over 90% silicate minerals, and silicate minerals like feldspar undergo incongruent dissolution or weathering, in which some of their ions like calcium, magnesium, potassium, and sodium are leached out or dissolved out of the mineral lattice first, leaving behind essentially clay phases. That's why feldspar weathers to clay, because clay is essentially what's left behind when all of those ions leach out of the mineral. It's just aluminum silicate, and aluminosilicates are clay minerals. And so because of this reaction, increased atmospheric CO2 and SO2 levels, which increase the amount of acid rain that falls onto things like soils that contain minerals like feldspar, these increasing gases in the atmosphere increase chemical weathering rates because they increase the amount of feldspar that is chemically weathered through reaction with either carbonic or sulfuric acid. And so, yes, the atmosphere can greatly affect the lithosphere, but can the lithosphere affect the atmosphere? Well, it turns out, yes, absolutely, it can go the other direction, but how? Well, there are actually many ways, but the most significant way that the lithosphere can affect the atmosphere, specifically climate, is through carbon burial and release. Carbon burial and preservation, in other words, the formation of carbon-containing rocks in the lithosphere, removes carbon from the atmosphere, and thus that causes cooling, because the more carbon you have in the atmosphere, the warmer it is due to greenhouse warming. Whereas the release of carbon from the lithosphere to the atmosphere through volcanism or impacts that impact carbonaceous sediment, or humans converting fossil fuel deposits, carbon-containing rock deposits, to atmospheric carbon, increase atmospheric carbon concentrations and cause warming. Carbon burial can occur in, well, a few different ways, but two main ways. Either through the burial and preservation of organic carbon deposits, like fossil fuels, or through inorganic carbon deposits, like calcium carbonate, limestone. Organic carbon becomes buried in marine sediments, most of the time, beneath algal blooms. Many organisms beneath the bloom decompose that organic carbon, converting it right back to CO2, but some of that organic carbon, at least in very productive blooms that are making a lot of organic carbon and increasing that sedimentation rate, some of that organic carbon does get by and get through without getting decomposed, and that has the potential to get buried and preserved in the rock record as organic carbon. Because organic carbon decomposition uses up oxygen, when organic carbon escapes decomposition and gets buried, this increases atmospheric oxygen concentrations, well, oceanic and atmospheric concentrations, because that oxygen was not used to decompose that carbon. The opposite occurs when organic carbon deposits or fossil fuels are burned or oxidized. In other words, because oxygen is used to oxidize organic carbon to carbon dioxide or convert it to carbon dioxide, oxygen concentrations decrease or go down as more organic carbon is converted to CO2. This leads to a kind of equal and opposite relationship between the carbon and oxygen cycles. Carbon sinks, or processes that cause carbon to become buried and preserved in the rock record, are things that typically cause oxygen to become released and increased in the atmosphere, and oxygen sinks are often carbon sources to the atmosphere. So these kind of work hand in hand, and we can see the way they've fluctuated and cycled kind of inversely throughout the rock record. Inorganic carbon, on the other hand, is often buried as calcium carbonate due to, or kind of indirectly due to, chemical weathering. Essentially, chemical weathering of certain minerals leads to the transport of calcium and bicarbonate ions to the ocean, where they can react to form calcium carbonate. And thus weathering can enhance carbon burial rates, and thus this can lead to long-term carbon storage in calcium carbonate minerals, carbon-containing minerals. This is also, like the algal bloom or organic carbon burial example, a negative feedback. In other words, it's something that balances the current increasing atmospheric CO2 trend. The more CO2 in the atmosphere, the more photosynthesis and algal bloom production, and the more carbon burial, which will decrease that carbon and cause cooling. And likewise, the more CO2 in the atmosphere, the more acid rain, the more chemical weathering, the more transport of ions to the ocean, the more deposition of inorganic carbon, and thus, again, carbon burial and cooling. A lot of people, however, think more CO2 in the atmosphere means more carbonic acid and thus more calcium carbonate formation directly from CO2 exchanging from atmosphere to ocean. But that's not actually how things work. Unfortunately, the reaction between CO2 and water obviously forms carbonic acid, which, when, reacting with calcium carbonate minerals, actually induces their dissolution. It pushes them over to the dissolving side of the equation, the more CO2 is present. So essentially, carbonate minerals buffer the ocean's pH. The dissolution of the carbonates takes up hydrogen ions. pH is just a measure of the concentration of hydrogen ions. The more hydrogen ions, the more acidic. The less, the more alkaline. And when this dissolution reaction, due to the increased acidity, takes up hydrogen ions, it therefore helps to stabilize the pH and keep it from getting too acidic. Likewise, mineral formation, the precipitation of calcium carbonate by increased pH levels, takes up hydroxyl ions, lowering and stabilizing the pH once again. Therefore, more CO2 in the atmosphere and thus in the ocean systems lowers pH and kind of shifts that equilibrium pH, because the amount of the buffer isn't changing, it's just the amount of the CO2 that's changing, and it shifts that equilibrium pH down. So the ocean is essentially becoming more acidic, which is really not great for reef ecosystems, because these animals make their skeletons, for the most part, out of calcium carbonate. And ocean acidification is not the only problem that reefs are dealing with. They're also facing warming, which is causing them to become bleached. In other words, the algae that they live with symbiotically leaves and they need that algae to live. And they're also facing ocean anoxia, or oxygen depletion, which is leading to not only reef devastation, but all marine animal life devastation, because they need oxygen to live. All animal life respires oxygen. Well, there's like some sponges that can anaerobically metabolize, but for the most part, they need oxygen. And I'll talk much more about this in my upcoming video or videos, I think actually it's going to be multiple, over ocean processes and changes and how that's affecting other systems. However, there is one way that we can actually combat ocean acidification and attempt to lower atmospheric carbon dioxide levels at the same time. The idea is to induce chemical weathering of a specific mineral called olivine, which I've talked about before. It's this beautiful green mineral in coastal and rainy regions. Essentially, the reaction of olivine with water and CO2 leads to the formation of bicarbonate ions, along with silicic acid and magnesium. And these things, when they get transported to the ocean, because it contains bicarbonate instead of carbonic acid, it actually leads to higher alkalinity and favors the formation rather than the dissolution of calcium carbonate. So while removing carbon from the atmosphere, this will actually also potentially lead to a slight increase, or kind of a competing increase in pH, while the other, the atmospheric exchange of carbon with the ocean is kind of competing to decrease it. So it will buffer the ocean's pH while we also aim to sequester carbon from the atmosphere. And this carbon over, very long time scales will eventually contribute to the carbonate and or organic carbon rock formation, and thus carbon burial and cooling. Now, chemical weathering is not the only way that the lithosphere can affect the atmosphere. There's also biological weathering. Microbes and other organisms break down complex organic matter into simpler ones. This happens a lot in marine sediments and in soils. And microbial decomposition releases nutrients like carbon compounds, nitrogen and phosphorus compounds back into the ecosystems for other organisms to use. And they often do so in a way where they convert those compounds into things that are more available or usable for other and higher life, like plants and then us. And this decomposition also, of course, converts some of that organic carbon all the way to CO2, which reacts again with water to form carbonic acid, like we've talked about, which again promotes dissolution and further chemical weathering. So in a way, biological weathering not only promotes weathering through direct microbial activity, but also indirectly through the, increase in acid production. So is there anything else? Any other ways in which the lithosphere can affect the atmosphere, the climate, or other Earth systems? Well, the lithosphere has played a huge role in climate over Earth's history by way of its evolving land surface. Essentially, its land surfaces have changed in composition and color and reflectivity characteristics throughout time, and the distribution of these things as well. For example, when plants spread over land, the entire land surface changed colors and thus absorption characteristics, and this led to differences in the water cycle, because obviously the absorption characteristics in terms of water were changed, but also in terms of light absorption and reflecting. And I actually have a video called When Earth Was Purple, where I actually talk about how on early Earth, it wasn't fully purple, disclaimer, but there was a lot more photosynthesizing organisms that actually used purple pigment to absorb light and photosynthesize instead of green chlorophyll pigment. And it's changes like these that have really changed Earth's surface, and therefore its light absorbance capacity and reflectance characteristics, which have changed Earth's temperatures, and thus, temperature that it receives from the sun and absorbs is kind of what drives atmospheric and oceanic circulation, and therefore the entire climate system. So it's really crazy to think about how interconnected everything is. The lithosphere has played a huge role in helping to control and maintain and perturb at sometimes climate throughout Earth's history. Another sort of recent example of land surface changes that have affected climate is the urban heat island effect. This is an effect that leads to cities having a higher temperature on average than the surrounding regions. And this is a big deal for how climate change might progress in climate models. And it's very interesting how, one, this is happening and what it might impact. But I'll talk much more about this in later videos in the next couple months. I'm not sure what it'll be titled yet, but I will talk about this. Lastly, the lithosphere has also played a role in inducing glaciation when land masses move over poles, or the opposite, when land masses are not over poles. For example, the modern ice age, the ice age we are currently in, was kicked off by two major events that helped to isolate waters and cool waters at the poles, which allowed for the development of our modern ocean thermohaline circulation conveyor belt, which transfers and distributes a lot of heat on Earth, controlling, in many ways, Earth's climate. And so continental distribution plays a big role. And I talk more about these events that led to our modern ice age in the onset of the modern ice age video, I think is what it's called. So I'll link that to the top right if you're interested. And if you want to see one more example of when land masses have moved over a pole, in this case the South Pole, and in part induced an ice age and eventually mass extinction event, you can check out my Ordovician mass extinction event. That one is all about that, as well as some other causes of that, but it did contribute. Anyway, I hope you guys enjoyed learning about how the lithosphere, or rocks, affects climate and other Earth systems in really intricate and detailed and interconnected ways that are super cool. So with that, thank you very much for watching. References are linked down below as always, and I will see you guys in my next video. Bye!